Okay, so here we're ready to start chapter 2. Let's start with the problem of the day from chapter 1, which absolute value inequality represents the graph shown below. And take some time, work it out, and pause the video. And then when you're ready to move on, you could resume the video. All right, so 2.1 is called represent relations and functions. All right, so now we're starting to get into x and y, not just one variable, two variables here. So we start with some basic terms: a relation, mapping or pairing of input values with output values. The domain is the set of input values. I also like to think of it as the x. I want to add that. And the range is a set of output values, or the y coordinate. All right? So representing relations, if we take a look at the key concept here at the bottom of the page, it says relation can be represented in the following ways. All right, so we have ordered pairs, x comma y. We have a table and a graph, and they all represent the same thing. All right? And I'm sure you're familiar with this at this point. So let's take a look at example 1. It says consider the relation given by the ordered pairs, which are 3 comma 2, negative 1 comma 0, 2 comma negative 1, negative 2 comma 1, and 0 comma 3. We want to identify the domain and range. Okay, so I'm actually going to type it in here with us. Now, a lot of times in math, more probably in trig than anything else, when you get to it, we like to use these little brackets, squiggly brackets there. Domain is all the what? The x values. So I like to try to order them from least to greatest as I go. So I have negative 2, negative 1, 0, 2, and 3. Once again, domain is all of the x values. All right. Range is all the y's. And I have them ordered from least to greatest. Not that you have to do it, but I find it easier to check when we do problems together to check our work. If we all have them in the same order, it's easier. And there's our range, negative 1, 0, 1, 2, 3. Now I ask you, is this relation a function? And let me fix that. Okay. Why or why not? If we take a look, the key term that you might want to write down is x's cannot repeat. So if I take a look at all of my numbers here, negative 2, negative 1, 0, 2, 3, none of them actually repeat. So I'm okay, so I'm right, yes. No, x's repeat. Okay, we'll talk more about what makes something a function coming up. Here's our term, function. A relation for which each input has exactly one output. All right. So each input. So I have a note here. If any input of a relation has more than one output, then the relation is not a function. So x's can't repeat. There's a couple ways we could look at it. Y's can repeat. That's okay. The output can repeat. The input cannot. So let's take a look at example 2. Graph the relation and tell whether the relation is a function. All right. So we're graphing our ordered pairs. Remember, and I have it labeled here. Here's the x axis. Positive x's are to the right, negative are to the left. Here's my y-axis. Positive y's are up, negative y's are down. So I have negative 5, 4. So 1, 2, 3, 4, 5. There's my point. Then I have negative 1, 0. So I go to the left one. Negative 0 stays there. 3, positive 1, 2, 3. Down 1 for 3, negative 1. And 1, 2, 3. Negative 2 is right about there, right? Okay. So we have to say whether or not it's a function. All right. Take a look, and there's two ways. Now that we see the different representations on that first slide, look at all the x's, right? I have negative 5, I have negative 1, 3, and 3. Uh-oh. 3 and 3 repeat, right? So because they repeat, we write no, not a function. Okay. Now take a look. Where's 3 and 3? Right here. See them above each other. So what if I don't give you the ordered pairs? We're going to take a look on the next slide, another way to tell whether or not something's a function by the graph. Can you find all the points, write them out, and check if x's repeat? Yeah, but there's a shortcut to doing that without having to do all that extra work. So let's take a look. It's called the vertical line test. We use the graph of relation to determine whether it is a function by applying the vertical line test. Okay, so the vertical line test, if we go back just for 1 second, go back. It means if I draw a whole bunch of vertical lines, up and down lines, I'll only hit 1 point. If you look here, if I drew this line through 3, look what happens, 1 point, 2 point. That's why it's not a function. So if we come back here, here's an example. It says a relation is a function if and only if the vertical line intersects the graph of the relation at more than 1 point. So see, this is actually a parabola. We'll get to that later on this year. But if I draw a whole bunch of vertical lines, I'm only ever going to hit 1 point. Here's the representation of like the red vertical line. But I would just draw a whole bunch of red vertical lines. That's a function. It passes it. If you look here, and this happens in more than one spot, but if I draw a whole bunch of vertical lines, here's one instance where look, 2 points cross through. All right, so if I hit more than 1 point with my vertical lines, now you don't actually have to draw them. I just think about as moving them around with my hand or whatever else with my eyes. If you hit more than 1 point, it's not a function. Okay, so let's look at this next one. It's the word problem. And I'll read it out loud. We're going to talk about whether or not they're functions, the graphs, just by looking at them using that vertical line test. So, first graph below plots average points per game versus age at the end of the 2003-2004 NBA regular season for the 8 members of the Minnesota Timberwolves with the highest averages. The second graph plots average points per game versus age for one team member, Kevin Garnett, over his first 9 seasons. And there he is off to the right. The relationship by the graph's functions explain. See what you can come up with first. All right. I want to pause the video and try it yourself. If I take a look here, I'm doing that vertical line test, as in I'm drawing a whole, actually let me use this again, a whole bunch of straight vertical lines. And any time I draw a line, it can't hit more than 1 point. And same with this one. All right, so if I look at this one, the answer is actually not a function. The one with Kevin Garnett is a function. All right, let me explain why. The issue with the one on the right, actually there's 2 issues. If I draw, I'm just going to draw a dotted line to not cut through the points. But here's 2 instances at ages 28 and 29. Now what do you notice? 2 points, and this one might be hard to see, but they sort of overlap here. I hit 2 points here and 2 points here using my vertical line test. So it's not a function. But that makes sense because if we're doing age versus points, if you have a team of 8 members, chances are at some point they're going to be around the same age, and as time goes on, ages are going to overlap. So it makes sense the input or age can repeat. Here for Kevin Garnett, it's a function, because think about it. It's only one person we're measuring. So we're measuring his age versus points. So he can't be 28 twice or 26 twice or whatnot. So that's why this one's a function, and the one with the group of 8 of them is not a function. Once again, using the vertical line test. All right, so the next part of the lesson, I'm going to take a look at equations. Equation 2 variables, functions of graphs. My example is y equals 3x minus 5. I sort of mentioned this already in the first slide with domain range, but here we're talking about them as independent and dependent. Independent variable, the input variable x. Dependent variable, the output variable y. Solution, the ordered pair x comma y that produces a true statement. Graph, all of the points x comma y that represent the solutions of the equation. So for the next one here, and I know you probably know an easier, more efficient way to solving these, but we're going to graph the equation y equals 3x minus 5 by using a table. All right, I'll give you a setup of a table here. Okay. So for x, I'm going to pick a couple numbers here. I'd say pick 3. If you had to pick, I would pick 3 or 5. I'm going to do 3 of them. I usually try to pick, if you do 3, which is the minimum, I'd use like -1 and 1 and 0. 0 in the middle, -1 to the left, 1 number to the right, +1. So we're going to plug in -1 for here. Let's see if I could draw so much straight line. All you have to do, and really if I ask you to make a table, a lot of times I give you the table, but if I didn't, you're allowed to pick whatever numbers you want. I don't know why sometimes that confuses a lot of people here. So how would I solve for these? Okay, I'm going to write it down here. Or actually, you know what? I think I'm going to type it like I've been. So say if I plug in -1, it's going to be y equals 3 times -1 minus 5. Y equals -3 minus 5. Y equals -8. So you're going to come back up here. Okay. And then I would do another one, wherever you want to fit them. So let's type here. Let's do 0. And I'm not going to show as much work in this one. You should get -5. Right. And actually, I'll do the other one already, and then we'll write them in the chart. So with the table, you get to pick what numbers you want. I always say at least 3 points, 3 to 5. It's your call, as long as you can see most of the graph. That's fine with me. All right. So here's our numbers. So let's type them in the chart here. All right. So -1, -8 is down here. 0, -1, 2, 3, 4, 5 is here. And 1, -2 is here. And because it's a line, now bear with me with my sort of crooked line here. We're going to connect the points, draw arrows going down to the left or right, or whatever you want to call it, in both directions. So here's my graph. And now, like I said, a lot of times I will give you the x coordinates and then you plug in the y. But if you had to make a table, you have an idea now of how to do that. Okay. So next, moving on here. Last one, linear function in function notation. All right, linear function can be written in the form y equals mx plus b. Function notation can be written in the form f of x equals mx plus b. So we're just replacing the y with f of x. Function of x is how I read that. F of x or function of x. So in order for something to be linear, it has to actually look like the form y equals mx plus b, a line equation. Just like if I go back for a second, this was y equals mx plus b, right? I have an x to the first power, I have a single y, all right? What you can't have, all right? Linear is a straight line. It's what you know to graph right now. It's what you know to solve right now from Algebra 1. It can't have an exponent greater or less than 1, well, greater than 1, or any -1, I should say. So you can't have a square, you can't have a fourth power, you can't have a root, you can't have a variable as an exponent. So any exponent that's not the 1, chances are it's not linear. All right? So it has to be in this form here. So if we look at example 5, which is the last one, tell whether the function is linear, then evaluate the function when x equals -3. All right, so if we take a look at our problem, how do I read A? F of x equals -2x cubed plus 5. Well, this one is not linear. As I was saying, this one is nonlinear, or not linear, because of one key thing here, and I'm going to underline it. Do you see how there's that little tiny 3, the cube? You can't have it an exponent that is not 1. So it's cubed. That is a different kind of graph that you don't know how to graph yet. It's not a straight line. So the other thing you could ask yourself, do I know how to graph this? And if you can't graph it, chances are it's nonlinear. Now, how do we solve with function notation? We want to also evaluate function x equals -3. So every time I see an x, I'm going to plug in -3 for it. So you see how that was an x here? All right. So I still have f of -3. That's how you say that. It's a notation that you'll see a lot more in math as time goes on. But take a minute and pause the video and evaluate it yourself. What you should get, and make sure you do this yourself first, because we do the exponent first, you should get 59. We do -3 cubed first, which is -27, and then continue on. All right. Now b, g of x equals 12 minus 8x. All right. This one is actually linear. I know we have the mx last, but that's okay. So it's linear, it's x to the first power. Once again, what's nonlinear? Any other exponent, if there's a variable as an exponent, absolute values are not linear, graphs, and so on. We'll talk more about it in class. Now take a minute and pause the video and try to solve this yourself. But g of -3, and we can use letters other than f. Later on in Algebra 2, you'll see if we have more than one function, we can't always call it f of x. We usually call it the first one f of x. But if there's more than one, we can't call them all the same thing. So we'll use a different letter like g. And see what you get when you evaluate that. You should get 36. So both of these, my final answer would be this bottom one here. F of -3 equals 59, or g of -3 equals 36. Okay. So for the last one here, that's it for the lesson. I know it was a little long. Usually the first lesson, each chapter has a lot of explaining and definitions and terms. Here's your homework. 6 problems. Read through them. You're probably going to want to write them on another sheet or somewhere further down. Make sure you answer them all. And that's it for this lesson.